Assalamualaikum warahmatullahi wabarakatuh. I'm Afika. I'll present the introduction for this experiment. So, first of all, this experiment is about flow measurement. In this experiment, the flow measuring apparatus is used to familiarize the student with typical method of the flow measurement of an incompressible fluid, and at the same time demonstrate the application of the Bernoulli equation. In fluid dynamics, Bernoulli principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in static pressure or a decrease in the fluid potential energy. The flow is determined using three different apparatus, which is ventrimeter, orifice plate, and a nozzle, and rotameter. The pressure drop associated with each meter is measured directly from the manometer. So the next one is the objective of this experiment. Our main objective for this experiment is to compare the discharge coefficient, which is CD, of different types of flow measurement methods. And the next one is to determine the relationship between the pressure and the flow and the velocity through different flow meters. And the last one is to investigate the accuracy of each flow meter and factor that contributing to error or inaccuracy.
Hello, I am Adzin. Today I will present the theory part. Before we go further, we see the slide first. Many types of devices using principle of Bernoulli equation has been developed to measure fluid velocity and flow rates. The types of flow rates that will be used in this experiment is first, orifice plate, second, nozzle, and third is venturi. Bernoulli equation states that increase in speed of the fluid occurs simultaneously with decreased pressure or a decrease in the fluid potential energy. This equation applicable when the fluid first, incompressible, second, inviscid, third, steady state, and fourth, along the streamline. The operation of each based on the physical principle whereby an increased velocity results in a decreased pressure. First, we will see orifice plate. An orifice plate is a restriction with opening smaller than the pipe diameter, which is inserted in the pipe, as you guys can see on the slide. Due to the small opening area, the fluid velocity will increase, causing a corresponding decrease in pressure. The flow rate can be calculated from the measured pressure drop across the orifice plate, P1 minus P2. The orifice plate is most commonly used flow sensor, but it creates rather large non-recoverable pressure due to the turbulence around the plate, leading to the high energy consumption. As you guys can see on the slide, the equation for theoretical flow rate QTH can be calculated by this equation. The discharge coefficient is defined as the ratio of actual flow rate to the theoretical flow rate. As you guys can see on the slide, coefficient of discharge can be calculated by dividing Q actual and Q theoretical. And then, actual flow rate can be calculated by this equation. Next, we will see nozzle. The nozzle applied the same principle and calculation as orifice plate. As you guys can see on the slide, the difference between nozzle and orifice plate are first, cross-sectional area of nozzle A2 and the shape of restricted opening whereby the opening is approximately a quarter ellipse. As you guys can see on the slide, the equation for theoretical flow rate QTH can be calculated based on this equation. The discharge coefficient is defined as the ratio of actual flow rate to the theoretical flow rate. As you guys can see on the slide, coefficient of discharge can be calculated by divided Q actual and Q theoretical, and then the actual flow rate Qx can be calculated based on this equation. Lastly, we will see Venturi. Venturi meter is a device for measuring discharge in a pipe. It consists of a rapidly converging section, denoted as a point 2 in the figure 3, which is increase the velocity of flow and hence reduce the pressure. It then returns to the original dimension of the pipe by gently diverging the diffuser. By measuring the pressure difference, the discharge coefficient can be calculated. Next, the equation for theoretical flow rate QTH for Venturi can be calculated based on this equation. Lastly, we will see the discharge coefficient for Venturi. The discharge coefficient is defined as the ratio of actual flow rate to the theoretical flow rate. The discharge coefficient can be calculated by divide Q actual and the Q theoretical, and then actual flow rate can be calculated based on this equation. That's all from me. Thank you. Next, I will pass to the next presenter.
Hi, I'm Aida, and I'm gonna present the apparatus and also the methodology of this experiment. So firstly, we will need two ventilation valves, which are in black and white. So we're gonna have two ventilation valves, and then we will need a rotameter, gate valve, multi-tube manometer, orifice plate, or we could call it nozzle. And we also need to have the water inlet and the water outlet. Next, we will need a venturi, main switch box, and the last one is the flow control valve. Firstly, we need to ensure that the orifice plate is properly fixed at its position and fasten the manometer tubes, which are H1 and H2, to the orifice plate. Number 2, we close the flow control and the gate valve, and then turn on the main switch and the pump. Number 3, simultaneously we slowly open the flow control and the gate valve until they reach their maximum opening level, which means that the water in the manometer will overflow. And then number 4, we open the black ventilation valve by turning it to anti-clockwise direction, so that if they have any bubbles in the system, we could release all of them. 5, we close the black ventilation valve, and then we close the gate valve. The pump was turned off, and then we slowly open the white ventilation valve until the minimum water level of 30 to 40 millimeters is reached, and then the pump was turned on. Number 7, we slowly open the gate valve until the level of water in H1 reached maximum 390 millimeters, and manometer H2 is at the minimum level. And we record all the readings including H1, H2, rotameter, and we also record all of the readings for the other 5 different values by reducing the opening of the gate valve. The minimum value of Qx should be around 200. Lastly, we close the gate valve and turn off the pump.
Hello, my name is Ahmad Zikri and I will present to you the result we get from the experiment. So as you can see, this experiment has used three types of methods, which is using orifice plate, nozzle and venturimeter. So for the first data for the orifice plate, the curotometer is in liter per hour, so we need to convert it to meter cubic per second by dividing 360,000. So that is for the Q actual, and then for the Q theory, as has explained in the theory part, it used the formula Q theory equals to A2 square root by 2G times H minus 1 over 1 minus A2 over A1 square. So that's for the Q theory part. So for the A1, the inlet pipe diameter is given, which is 0.032. So from there we can find the area, which by using the formula pi r square. Same as A2, the orifice diameter is given, which is 0.0185, and then we just to find the area we need to use the formula pi r square. So as for H1 and H2, the result is from the experiment. So to find the difference in H, so we just H1 minus H2. And last, for the coefficient of discharge, the Q actual divide by Q theory. Okay, so for the data for the nozzle, same as the previous one, the curotometer is given but in liter per hour, so you need to change the unit to meter cubic per second, same as previous. And then Q theories use the formula given, and for the A1 and A2, the inlet pipe diameter is given and the nozzle diameter is given, so we can find the A1 and A2. And for the differences in H1 and H2 has been calculated from the has been recorded from the experiment, so we can find the differences in H. And the last one of the coefficient of discharge, just divide Q actual divide Q theory. Okay, so for the last data, which is for the venturimeter, same as the previous one, the curotometer is given, but it is in liter per hour, so we need to change it to the meter cubic per second. And then for this data, the area of venturi 1 and 2 is given, so we don't need to calculate by using the pi r square, because it is already given. And for the differences in H, is same, just H1 minus H3, and then for the coefficient of discharge, the Q actual divide by Q theory. So that is all from me. Thank you.
Thanks, Yao. Now I will continue to present for the discussion. The first topic is about the difference in discharge coefficient value of each of the flow meter and the ranking of flow meter according to the accuracy. To explain this problem, we decided to calculate the coefficient of discharge, which is the CD, for each meter. We also pointed the graph by using log fault rate actual and log height difference. Based on the data, the CD of orifice plate is 0.319, nozzle is 0.584, and venturimeter is 0.913. And based on the graph, we also found that the graph line of orifice plate has huge difference with the trend line. So based on the graph, the line of orifice plate is extremely different with the trend line. The result is having low precision. The position of venturimeter and nozzle can be trusted since the graph line is almost same with the trend line. The average CD value of venturimeter is 0.913, which is the closer to 1 compared with nozzle and refill plate. The average CD value of nozzle is 0.584, which is slightly smaller than 1. There are some errors happen during the experiment. The average CD value of orifice plate is 0.319, which is so much smaller to 1, shows that the actual flow rate is so much different from the theoretical flow rate. The most accurate flow meter is venturimeter. The accuracy of flow meter is venturimeter above nozzle above orifice plate. Next, we are going to discuss the difference of water level in manometer with different type of flow meter. Based on our data, H1 is always greater than H2. Meanwhile, our flow rate is our concern. So we are going to use the Bernoulli equation to discuss about this topic. Since the inlet and outlet placed at same height, that means our Z1 is equal to Z2, so we are going to remove the both Z in our equation. According to the equation, flow rate is equal to area times V velocity. Since our area outlet is smaller than area inlet, our velocity at outlet is bigger than our velocity in inlet. That means there are some kinetic energy lost due to the surrounding and the friction, and our pressure are going to lose to balance the Bernoulli equation. Hence, our pressure at outlet is smaller than our pressure in inlet. So based on the equation of pressure is equal to rho GH, our H1 is always greater than H2. The last topic is about the factor contributing to error and inaccuracy in experimental data. First of all, there are some water leakage between the tube and manometer due to the poor connection, and due to some air bubble in apparatus, it will give the wrong height of manometer. Other than that, the flow rate is unstable, hence the height value keeps changing and gives the wrong reading. After that, the imprecision of using stopwatch to record time gives us many trouble. Furthermore, water minuscule causes the reading of the manometer slightly hard. Lastly, parallax error due to the observer eyes are not aligned with the reading of meter. So, there are some recommendations for us to minimize the error. The first one is giving some time to let air bubble escape from the flexible tube totally until empty to give a perceived reading. We also need to ensure the water source to give a constant flow during experiment before opening the valve during the experiment. To avoid parallax error, the observer eyes should be perpendicular to the scale. Then, the readings should be taken repeatedly and take the average value to minimize the error. We also suggest to use digital stopwatch to record the time. Lastly, ensure the surrounding is safe and will not affected by the natural conditions such as wind blows. Thanks, I'm going to pass the present to my roommate.
The last part for this experiment is the conclusion. After completing this experiment, the objective to compare the discharge coefficient, which is CD, of different type of flow measurement methods is obtained. Different type of flow measurement leads to different discharge coefficient because of sudden expansion or sudden contraction, which is its affect the velocity of the fluid. When the flow rate increase, its velocity will increase and result in a decrease of pressure. The next one is for the most accurate flow measurement device is venturimeter. This is because the venturimeter has discharge coefficient that approximately 20. And the last one is there are some errors such as systemic error and random error while doing this experiment. And to avoid this error, we can do the precaution that have been presented by Chua. So that's all from us. Thank you.